next installment in this business of circular motion and or centripetal forces, I'd like to talk a little bit about vertical circles, and more specifically, we're going to talk about, well, roller coasters. And so perhaps we've all ridden a roller coaster before, and we're familiar with something that has maybe a vertical loop to it. And so a vertical loop, this is pretty circular. I guess I could do a little better, but we're going to find this vertical loop also has a radius, right? And this radius I could generate from anywhere in the circle. And in fact, if I generated the radius and I look straight up, right? And I guess the most intense point in a loop on a roller coaster is when you're directly upside down. Because when you're directly upside down, there's where you have the ability to perhaps fall out of your seat. Now, if you're going to fall from your seat, that means that you have to have a force pulling you down that's greater than your weight. And your weight is represented as Fw. Well, the centripetal force pulls to the center of the circle, but directly opposite that is the centrifugal force, which presses you up against maybe the seat, I suppose, when you're upside down. So in a vertical circle, Fw, at its minimum speed to keep you in your seat, would have to equal whatever the centripetal force happens to be, which is Fc. And so this one's a little simpler than maybe friction. And I always say that because, well, Fw is representable as mg, and the centripetal force is mv squared over r. And so I end up with something that's pretty easily solvable for v. I'm just going to bring it over here so it looks a little easier to do some mathematics with. Again, we look at this and say, well, mass can cancel out, it becomes immaterial at this stage. And then I believe one of the things we're most interested in is velocity, but we could also solve for r if we'd like. Solving for v is relatively easy. I just end up with v equaling radical rg. And heck, if you wanted to solve for r and g will switch places for you, and you can end up doing v squared over g if you wanted to do that as well. Now, one additional scenario that I'd like to share with you is orbits of planets and or satellites. And this is something that, well, another type of force that we've studied in the past that then can revisit in the centripetal motion business. So we've got our Earth, right? And I always say that because this is usually what we think of as satellites orbiting. And so we perhaps have a satellite that's orbiting the Earth, right? And let's put some little solar-powered doohickeys off here, and it's transmitting to Earth. Well, we're going to have a distance, right? And so here is a distance that this satellite is from the Earth. However, the satellite itself is traveling in a circle around the Earth, right? But what is the satellite really doing? Remember, it's traveling in straight lines, and then there's a force that's continually pulling it towards the center of a circle. And so the satellite's continually going in a linear velocity, but changing direction, which requires a force. And that force that keeps pulling it back towards the center of the Earth is in fact gravity. And so we're looking at F sub g. However, you may remember that gravity is a function of how far away from the planet's surface we are. And this thing's traveling in a circle, but we can still look at this in terms of how far are we from the center of the Earth. And so F sub g, you may remember, is big G, m1, m2, distance squared. And not only is this distance important, but also the radius of the Earth. Which happens to be 6.37 times 10 to the 6th meters. So we do have to consider that as well as the height that the satellite is found at. And that would get us our total distance maybe in this equation here, right? Well, if the satellite's going to move in a perfect orbit, then the gravitational force has to perfectly equal the centripetal force. And so what I'm going to do is say, well, therefore, Fg must equal F sub c. And we're probably pretty indoctrinated to the idea that F sub c is mv squared over r. So let's set these two equations equal to one another, in which I'll take big G, m1, m2 over the distance squared equals mv squared over r. Now this takes a little bit of thought. First off, when we're talking about our satellite and the Earth and the gravitational pull between them, one of these masses is the Earth, and the other mass is the object. And so of these two masses, one is the Earth, one is the object. Well, if we look at the other side, this mass, when we're thinking about centripetal force, is in fact the object. And so what I can do is if this m1 and this mass could both be considered the object, then look, I can cancel those two out. I want to be consistent and use my nice red pen. So I'm canceling one of the masses because this m, that's part of the gravitational equation, is in fact representative of the satellite, and that is exactly what's moving in a circle, so it itself is still the satellite, whereas m2 is going to have to be the Earth in this case. Now, another simplification we can make is, really, what's this satellite doing? It's moving in a circle in which the radius of its circular path is the radius of the Earth added to this distance, which is exactly what d2 is when you really think about it. d2, or d squared that is this entire distance. So this r, which is the radius of the path of the circle, and this d are also the same thing. Again, let's simplify this by canceling this. Now, I cancel the r and I cancel one of the d's because this was d squared, right? And so what I'm ending up with here then is I have big G, I've got this m2. This m2 is the Earth, and then I've got over the distance. So this cancels out pretty nicely to become big G, mass of the Earth, over the distance equals d squared. At that point, I can take the radical of both sides, and I can end up with a working equation in which the v equals radical big G m sub e for the Earth over the distance. And this will solve me the minimum velocity associated with the path of this satellite so that it remains in orbit. You may also be able to appreciate the fact that once we get to f sub g equaling f sub c, we could still solve for other things if we really had to, but I mean, it's either we're solving for the distance or solving for the velocity. And I think maybe both are apparent in problems that we work on. Have some fun with it. I hope you enjoy.